Welcome back, everyone, to the start of Part 5 of this 5-part series on mathematical modeling of organic contaminants and subsurface remediation. In this final part, we'll take a look at a final case study involving simulating contaminant behavior in discretely fractured porous media. This study started with a site in Fergus, Ontario, just north of Kitchener-Waterloo, with my colleagues who were interested in this site. It was a hydrocarbon spill, a former gasoline station, and they were interested in looking at ways to enhance the degradation of the hydrocarbons by injecting oxygen, and eventually that's led to other areas of interest too. But for now, we'll look at the behavior of these contaminants in a discretely fractured dolomite rock. So the site here is in Fergus, just north of Kitchener-Waterloo, where they did this dissolved oxygen injection test. Just a bit of geology here. We're looking at the dolostone aquifer, a fairly porous and highly fractured system. Here's an outcrop near Guelph. So the site, here's a plan view of the site in Fergus. These are concentration contours of petroleum hydrocarbons, the F1 and F2 fractions in 2007. So a field test was set up in this area, and where they injected dissolved oxygen at very high concentrations using a special apparatus under high pressure, high concentration oxygen to look at the behavior of oxygen and see if it could be used to enhance the dissolution of these hydrocarbons. A bit later on, the plan was to inject oxygen or different enhancing agents, including persulfate, several injection wells along here. This was another site. We'll focus on this single injection well for now. So here's just the background again. There's a former gas station, fractured dolostone, and we're using this gas infusion technology where oxygen is injected into this discretely fractured rock under high pressure and high concentrations, and they monitored the behavior of oxygen in this down gradient well, about 3 meters down gradient, at these isolated monitor positions here. So the numerical simulation approach, we'll be using the Bionapple 3D model as we did in previous cases. This is an example of a coupled model, again, with multiple components, but also multiple media. In fact, this is a porous media superimposed with discrete fractures. So we can simulate the groundwater flow and mass transport equations on this porous media mesh, and we can superimpose these planar fractures as well. The fracture velocities are given by the cubic law. So just some more information on this discrete fracture model. We can generate a random fracture network here. We'll have flow coming in on the top and horizontal flow as well. Basically, in the matrix, we have diffusion-dominated transport, but in general, depending on the conductivities, we can also have advection in the matrix. But in general, if you have some contaminants coming in here or an electron acceptor, you'll have dispersion into the matrix from the fracture, and dominantly advection in the fracture itself. In general, we can have different phases as well. And at long term, if our source is cut off, or if our oxygen or electron acceptors are cut off, we'll eventually have this back diffusion effect where the mass from the matrix will then tend to disperse or diffuse back into the fracture, where the velocities are high here and the concentrations are low. So our gradients become reversed. But this is all handled by the model, because the dispersion coefficients, the dispersion terms, depend on these gradients of concentrations, which are all calculated by the model. So this is a conceptual model we'll be using for the simulation. For this particular case at Fergus, here's the setup. We designed a grid, and here's the flow system with the boundary conditions and the transport system for oxygen injection and boundary conditions. So we fixed the heads at the up gradient and down gradient faces, so we get a gradient that we like. Some recharge across the top. This is the top of bedrock. Here, there's a few meters of overburden as well, but we'll just be simulating the bedrock. And we can superimpose half a dozen fractures along here as well. For the transport, we need fractures as well, and we're going to be injecting the oxygen in this injection well right here. The mesh is refined near the injection well again to reproduce the high gradients that are likely in that area. And here's our grid, again, fine grid around the injection wells. We take advantage of symmetry as well. We have an injection well that we can put on this up gradient, or this near face. And assuming a symmetry, this will half our simulation time. So to calibrate the model, we've got some observed concentrations of oxygen in this down gradient monitor well at these isolated or packed off intervals here. So here's the simulated oxygen concentrations over time at these 6 or 7 monitor wells here. So this is just a visual comparison, and we reproduce the peak concentrations of about 30 milligrams per liter soon following injection, and we get rapid decay of these concentrations due to the short injection time of the test, but also due to diffusion into the matrix. This test case in the field was the oxygen was only injected for about 2 hours. So there's the injection time here and then decay. Here's a series of 3D images of that same calibration. So we have here the oxygen concentrations in grams per liter. So here about 22 or even up to 30 milligrams per liter in the injection well and around the injection well into these fractures. So this is immediately after the end of injection. And then we can take the model in time and look at behavior in time after half a day, up to 3 days, up to 5 days. So we see these oxygen sort of plumes or disks migrating rapidly down gradient depending on the fracture aperture. As the fracture apertures here are higher in these upper fractures, these fractures get washed very quickly and those plumes disappear, whereas the oxygen tends to stick around a bit longer in these smaller fractures, smaller aperture fractures down deep. So this was our calibration run, and we can take this further in time, but a better advantage maybe with the model, we could test different longer injection times to see how long oxygen will last in the porous matrix in order to degrade the hydrocarbons there. So here's exactly the same simulation, but now with a 7-day injection period. So here's the result of the injection immediately after 7 days. Injection was stopped after 7 days, and here's the simulation continued on to 100 days. So we can see now with a 7-day injection, we've got excellent dispersal of oxygen into the matrix and fractures. After 100 days, we can see the fractures are being washed now because we've got sort of lower oxygen concentrations coming from up gradient, so the fractures are washed, but we get oxygen remaining in the matrix. And this was helpful to understand the utility of this methodology and in this type of fractured rock environment. And in this case, we think oxygen could be available into the matrix at longer time to degrade the hydrocarbons there. And again, some other tests here, we can see gradients are well reproduced, high gradients along the fracture edges, again because of our low dispersivities and a high grid resolution here. We can take this conceptual model a little further and look at some more complicated fracture networks and build in different reactions as well. Here's a case of biodegradation in a fractured rock based on similar properties to that at Fergus, but now a more conceptual type of source zone. We have a source zone of benzene here already within the fractured rock, and this is dissolving. So here's benzene after 20 days in this fracture network after 50 and 100 days. In the same simulation, we can plot the oxygen consumption over time and the growth of the microbes over time. So here we see all kinds of interesting effects. We've got diffusion into the matrix quite extensively here, although in down gradient we've got some of the matrix zones, some of these matrix blocks still quite free of benzene. After 100 days we can see the benzene in the down gradient area has completely been flushed out or degraded, yet some remains in the matrix blocks in the source zone. Oxygen consumption is highest in that source zone, where it's almost completely consumed by the degradation processes, and yet down gradient we still see some zones where there's Still some oxygen persisting down gradient. And the growth of the microbes as well. So you get complicated systems like this, discrete fractures, nonlinear degradation. Modeling is a very useful way to gain insight into these properties, into this behavior. Here's the same simulation. I have an animation to show. What we'll be seeing is this, based on this 50-day snapshot, we'll be seeing the evolution over time. So in this top one, we've got benzene, toluene, bulk, all the remaining components, as well as oxygen, nitrate as another electron acceptor we've added, and the total microbial population. So what we'll see is the evolution of these three plumes, again, depending on their solubility and on their retardation, and the consumption of the electron acceptors and growth of microbes. See if this works. Here we go. So this happens quite quickly. Benzene's quite rapidly dissolved. It's very soluble. Toluene takes a little bit longer, as well as the bulk. Oxygen is being consumed by these three components. So we see its complicated behavior here. The nitrate is also being consumed by the three components and the total microbial growth pattern. So we can test this model. We can change properties, change porosity, see how this type of reactive system behaves under different conditions very easily once the model is set up. So that's more or less the conclusion. Just some summary statements here on transport modeling. Some critical issues. First, develop a good conceptual model of the flow system. Always keep realistic objectives in mind and proper use of models for gaining insight, scenario testing, and data needs, for example, rather than absolute predictions. Some remaining challenges: coupled biodegradation and geochemistry. This is a growing field looking at all the geochemical effects of these type of reactions. Reaction rates and the other data needs, often difficult to obtain, although modeling itself can help constrain these rates. Validating a conceptual model. There are not just one conceptual model you can prepare. Perhaps there are several conceptual models that can be tested. And the computational demands become a bit of a challenge with these large systems, fractured systems, multi-components in 3 dimensions. Lenconico, in a recent paper, summed it up quite well in terms of transport modeling, and that is to lower your expectations. Don't expect too much. Always keep in mind it's a simplified system, but modeling can be very helpful. I've listed a few references here for these studies I've shown, these case studies, and a longer list here of suggested reading. Many of these concern philosophy of modeling, how to develop models, what they're used for, some very interesting papers here, the role of models. So with that, I'll leave you with this statement from Stephen Hawking, that you can never say if it's the right model, but only that it's a good model. Hawking was speaking of models of the universe, but this applies equally well to our humble groundwater flow and transport models. If it's a good model, it has served its purpose, it has helped gain insight into some processes, and just some acknowledgments of help along the way. And with that, I'll end this part 5 of 5, and thank you for listening. Have a good day.